we present Sketch2Model, view-aware 3D modeling from single freehand sketches. Imagine you are in a VR or AR scenario. You have an object pictured in your head, which can be represented as a sketch, and you want it to be placed in the virtual scene. Now the problem is how to transform the sketch into a 3D object. However, existing methods fail to provide customizable and easy-to-use 3D modeling tools for novice users in this content creation scenario. Evocative methods create models from template primitives or retrieve objects from model collections. They are defined to generate certain shapes. Constructive methods directly map the input strokes to a 3D model, but it's very time-consuming to create a non-trivial shape, like the one taken from fiber mesh below. In this work, we investigate the problem of generating 3D meshes from single freehand sketches. This is not as straightforward as it sounds. Ambiguities commonly exist due to the simplifications and distortions of freehand sketches, like the camera shape ambiguity shown in the picture. Sometimes, even humans can't tell which side of the object is a sketch depicting, let alone computers. To alleviate the influence of shape camera ambiguity, we propose a view-aware setting where the user inputs a freehand sketch and optionally a viewpoint. The viewpoint can also come from network prediction and describes which angle the object is sketched from. The output is a 3D mesh. It will match the input sketch at the viewpoint. Let's start from a typical encoder-decoder architecture for single-view reconstruction. The encoder is used to extract image features from input sketch I, which are processed by the decoder to get a 3D model. A differentiable rasterizer R is utilized to guide the training process by comparing silhouettes of the input sketch and the output model seen from the ground truth viewpoint V. This silhouette difference is measured by intersection over union, shown as LIOU in this figure. To make the network depend both on the input sketch and the viewpoint, we first design a disentangled architecture shown here. EV and DV are view encoder and decoder, which maps the viewpoint to a higher dimensional space and backward. We encode the input sketch to a view-related feature ZV hat and a shape-related feature ZS. We get the view-related feature ZV from ground truth viewpoint V and try to combine it with ZS to get a predicted model. There, we made the viewpoint V as an input to the network, which you can replace with any other viewpoint rather than the ground truth one. Unfortunately, this doesn't work. The disentanglement fails because we only train the model on the ground truth viewpoint. The network does not seem to learn what the input viewpoint means. It produces ground truth shapes with ground truth viewpoints and get confused with other input viewpoints, like in this figure. We solve this problem by a simple but effective strategy, which we term random reinforced training. Except for the ground truth viewpoint V, we feed the network with the random viewpoint VR and force it to produce a 3D model that matches the input sketch at this viewpoint. This aims to encourage the network to generate shapes matching the given sketch at arbitrary viewpoints. Like is shown in this figure, we expect to get a different table, but with similar silhouette at viewpoint VR. This still brings problems. Obviously, we can't interpret a sketch at any arbitrary viewpoints. Non-feasible viewpoints will cause the network to generate distorted shapes, which only satisfy the silhouette constraint, but are not meaningful objects. Therefore, we propose a shape discriminator. It regards shapes from ground truth viewpoints as real ones, and those from random viewpoints as fake ones. We train the shape discriminator with a gradient reversal layer adversarially. With the shape discriminator, The network will always produce plausible shapes while trying to meet the silhouette constraints as much as possible. Here we illustrate the view-wheel property of our method. Our method outputs different shapes according to different input viewpoints, and ensures consistent silhouettes at these viewpoints. Take the table for example. If seen from the side of the table with a small elevation angle, the synthesized result will have a thick top and short legs. As the elevation angle gets larger, the tabletop gets thinner and the legs become longer to satisfy the silhouette constraint. Here we show the generation results of our method using predictive viewpoints on sketchy dataset. Our method tends to produce 3D shapes better matching the input sketch. We quantitatively demonstrate this in the paper. Also, our model generates reasonable results for out-of-distribution data, like the car in the table. To further evaluate our method, we collect a ShapeNet sketch dataset containing 1,300 freehand sketches drawn by novice users and their corresponding 3D models. The dataset is available online to inspire further research. Here we show comparisons on our dataset. For more information, please read the paper and visit the webpage. Thank you for your attention.